No man is an islet, separate entire to himself, but each is a lesser part of the pancreas. Well, that's why they're called islet, because they look like little islands. Even this picture exaggerates how much of it is actually islet cells. Did you know that islet cells are only 2% of the pancreas? 2%. 60 or 70% of islet cells make insulin. About 25%, 20% of it is alpha cells making glucagon. And 5 or 10% is delta cells making somatostatin. But islet cells look like little islands inside the exocrine pancreas. And that's why they're called islet cells, because they're islets in the pancreas. The islet cells make the insulin, but really the vast majority of the pancreas is an exocrine organ. So the exocrine part, the part that makes bicarb-rich fluids, is 80 to 90% of the pancreas is exocrine. Only 2% is islet cells that make hormones. Insulin, glucagon, somatostatin. Insulin, glucagon, somatostatin. But 80% is exocrine. Exocrine means through a duct. This is one of the most frequently incorrectly answered things when people don't realize how much of the pancreas is not endocrine. It is predominantly an exocrine organ. The exocrine tissue is in acini and ducts, and cholinergic nerves do stimulate secretion of both the enzyme and the aqueous component. However, the major thing that stimulates the pancreas is not really in response to acetylcholine, it's in response to hormones. Food in the stomach stimulates stretch receptors and a very small secretory volume. The sympathetics do inhibit secretion, and that's because when it's time to run away from dinosaurs, it's the wrong time and sit down and have a nice long lunch and have pancreatic secretions. Also, pancreatic secretions are enormous in volume. Did you know that your pancreas can make 2 to 3 liters a day from the teeny little organ? The pancreas is by weight a very tiny organ. It's only 50 to 75 grams. It's 28 grams to the ounce. The whole pancreas is 2 or 3 ounces. Tiny, but it makes 3 liters of pancreatic juice. Isn't that amazing? My goodness, how can this small organ make all those secretions? Well, because it can. So the pancreatic secretions are enormous, 2 or 3 liters in volume per day, and most of it's controlled by hormones. So when the question says, what is the greatest stimulant to pancreatic secretions? And as it says, is it endocrine, or is it hormonal, or is it neural, or is it paracrine? You say the major control of the pancreas is hormonal. Secretin makes the bicarb portion. Cholecystokinin makes the enzymatic portion. Secretin makes the bicarb and fluid portion. Cholecystokinin makes the enzymatic portion. The enzymatic portion starts out with trypsin. Now, trypsin actually starts out as trypsin-O-gen. And step 1 is very big on you knowing what is secreted in active and inactive form. Anything that says O-gen, of Genesis, is in inactive form. Inactive form because it has to be activated in the duodenum. We can't activate it inside the pancreas, because if you activate it inside the pancreas, it will chew up your pancreas. As a matter of fact, if you activated trypsinogen while it's still in your pancreas, that would be called a disease. The disease of activating trypsinogen prematurely is called pancreatitis. Pancreatitis is when trypsinogen is activated before it hits the duodenum. So trypsin-O-gen is secreted in inactive form and is activated in the duodenum. Once it's activated in the duodenum, the trypsin will basically activate the other enzymes. It will activate the chymotrypsinogen, the elastase, the carboxypeptidase. So trypsinogen is made in inactive form. It is activated by enterokinase on the wall of the duodenum. If it's activated prematurely, it's called pancreatitis. Deficiency of trypsin is like deficiency of all of them because trypsin activates the elastase, carboxypeptidase. and chymotrypsin. So diets high in protein generally result in a preferential production of enzymes for the particular substance. Proteins for trypsin, carbohydrates for amylase, fats for lipase. So pancreatic fluid also has ribonucleases and deoxyribonucleases to help process proteins. Pancreatic amylase is made as an active enzyme that you know is active because it says ACE. It's active because it says ACE. Lipase is active. Amylase is active. And it manufactures this as an active form because your pancreas is not made out of bread. It's not made out of starches, not made out of carbohydrates. So amylase can chop it down to a disaccharide, maltose, a trisaccharide, maltotriose, 3. Alpha limit dextrans is 4, 5, and 6 glucoses. 2 glucoses, maltose. 3 glucoses, maltotriose. 4, 5, 6 alpha limit dextrans. Well, why can't it metabolize it down to monosaccharides? Because it can't. You need the maltase on the brush border. That's why you need maltase, lactase, sucrase. Maltase, lactase, sucrase on the brush border. It also shows you why it is that you don't lose weight when you're lactose intolerant, because there are 2 other disaccharides to absorb, plus there's lipase to absorb the fat and all the protein digesting enzymes. But deficiency of pancreatic amylase is fatal. If you have no pancreatic amylase, you'll die. So you need to know, trypsin is inactive when made, trypsin-ogin. Amylase is active when made, amylase active. And that it won't metabolize, amylase will not metabolize it down to something that can be absorbed because you can't absorb disaccharides. You can only absorb monosaccharides. Now, how come you can't eat the New York Times? Why can't you chew it? It's made of basically a fiber, isn't it? Yeah, but you see, its linkage is in the other way around, so you can't absorb it. You can't absorb that sort of cellulose, and that's why we can't live on wood chips like a hamster. Well, that's why we can't go out in the North 40 and graze, because we just don't metabolize the cellulose linkages, but cows can. Horses and ruminants can. Ruminants can, because they have a different form of amylase than we do. Now, amylase and lipase are active because the pancreas is made out of protein, so they can be made active. It won't dissolve it. Now, if you're a gingerbread man would have to secrete amylase in inactive form. So gingerbread men would all get pancreatitis if amylase was activated prematurely. But since we're made out of protein, not out of bread or gingerbread, we can secrete our amylase active. Pancreatic lipase is active. You could split off a free fatty acid off of cholesterol with the cholesterol esterase and secrete it active. Colipase is something most people don't understand. You see, you need colipase to push the bile out of the way so that the lipase can touch the fat. Other than that, bile covers up the fat with all this goo. You need colipase to push it apart. It pushes the bile salts away on the micelles so the pancreatic lipase can touch it. Now, you get 2 free fatty acids and 1 position 2 monoglyceride. A 1 monoglyceride means that the second carbon, you have a fatty acid. You take off the fatty acids on position 1 and position 3, and you're left with position 2 monoglyceride. And that's what you get so you can absorb it. Now, sometimes people don't understand. Why do I have to do that? Why do I have to take a free fatty acid off of a cholesterol? Why do I have to have cholesterol esterase? Why can't I just absorb it as one big thing? Well, that is because you can't get it through the wall. You break it down into pieces, then you re-esterify it once it comes into the body in the lacteal and a chylomicron. And that's the same way you can't move your house as one big unit. You have to break it up into all the pieces, and then you re-esterify your house after you move it. You have to put it into boxes, then bring it back into the house, and then you re-esterify it. Same as putting it in a moving truck. So chylomicrons and your lacteals are like a moving truck for all of these digestive nutrients. They help you bring things into the body. Pancreatic proteases are secreted as an inactive zymogen. Zymogen is a $5 word for inactive enzyme. So it goes that trypsinogen is a zymogen. Ogen means of genesis, of creation. The enterokinase is on the brush border. So it may not be a brush border enzyme, but it's located in the lining of the small intestine. So it's a bit of semantics there. It's not technically called a brush border enzyme, but it is located on the lining near where the brush border is. So trypsin also activates chymotrypsinogen and also procarboxypeptidase and elastase. So if you're deficient in trypsin, it's like you're deficient in all of them. Now, you need only one amylase to absorb and digest all the starch. You need only one lipase to digest all the fats. But you need several different protein digesting enzymes. Well, this is because the bonds between the glucose molecules are everywhere equal. So no matter where you cut it, you only need one enzyme. And in the fat, the bond is everywhere equal, so you only need one lipase. But the bonds on the proteins between the amino acids are not everywhere equal. See, that's why you need a bunch of different enzymes to cut those bonds in amino acids. See, when you're cutting bread, you only need one bread knife, because no matter where you cut the bread, it's equally bready. And you only need one butter knife to cut the butter, because no matter where you cut the butter, it's equally buttery. But when cutting proteins, when cutting meat or chicken, you can't just use one knife to cut it, because although the bread is equally bready and the butter is equally buttery, the chicken is not everywhere equally chickeny. And that's why you need multiple enzymes to cut proteins, because the bonds between the amino acids are different. The fluid electrolyte components of pancreatic juice have an aqueous component that's secreted by the epithelial cells that line the ducts. Remember we said that gastric secretions are very acidy, so the gastric venous blood is very basic. Well, the product of the pancreas is very basic, so the acid goes out into the veins. The fluid's isotonic, and there's a high permeability of the duct to water, and the concentration of the sodium and the potassium are the same as plasma. Chloride secreted into the duct lumen, so it exchanges with bicarbonate. But the major product of the pancreas is bicarb-rich fluids, not insulin. The chloride goes across the apical membrane with a CFTR chloride channel. This is what gets damaged when you have cystic fibrosis. And the gene that encodes for this channel is damaged. And what ends up happening is that you just don't make much fluid in there. It gets thick and inspissated. The same thing happens in your lungs. And that's why you don't get the liquidy secretions and they clog up and you get pneumonia. Same thing happens in the pancreas, the lungs, the testicles. And basically it gets clogged up. It's kind of the opposite of cholera. Cholera is where it's switched on, and that chloride channel has excess chloride in fluid, and you start pooping your brains out, start peeing out your booty because you're making so much chloride and so much water going across. The opposite of cholera is cystic fibrosis, where things become all clogged up. The control of pancreatic secretions is predominantly through hormones. Cholecystokinin does the enzymatic portion with fat and amino acids. Well, you might say, why do amino acids make the cholecystokinin go up? Well, amino acids make the cholecystokinin because cholecystokinin also secretes the trypsin. So that helps you make the amino acids. Parasympathetic does happen, but it's small. Now, the initial secretions are high in bicarbonate, and secretin makes it even more so high in bicarbonate and more high in fluids. Now, this slide is simply a recapitulation of the other things we've said, which is cholecystokinin for the enzymatic portion and secretin for the bicarb portion. Now, cholecystokinin also has effect on the gallbladder. That's what the word means. Cholecyst means gallbladder. Kinin means action. So in addition to these enzymes from the pancreas, it also makes the gallbladder contract and the sphincter of Oddi relax and open, all from cholecystokinin. Pancreatic secretions are controlled also by secretin, which is released from the duodenum in response to acid. Acid touches the duodenum. The duodenum makes secretin. Secretin makes the bicarb. It stimulates chloride entry into the lumen from the duct cells. And the G protein has several components to it. The stimulatory protein portion of it makes cyclic AMP. Simply saying that cyclic AMP is the second messenger for the G protein that gets stimulated by the secretin. Now, the pancreas then releases the fluid high in bicarb, which neutralizes the acid. It neutralizes the acid because amylase, lipase, and trypsin do not like to work in an acidy environment. Acid would inactivate pancreatic enzymes. The same way that pepsin needs acid, trypsin, chymotrypsin, elastase, amylase, lipase need a much more basic environment. Cholecystokinin is released from the duodenum, and what ends up happening is that fat, peptides, amino acids, well, what's a peptide but a piece of a protein? What's amino acids but a piece of peptides? And when the fat touches the duodenum makes cholecystokinin. And then the pancreas releases all the enzymatic portions of things. Well, what ends up happening to all those enzymes after they chop up the food? What happens to the amylase, the lipase? You consume them. Isn't that interesting? The amylase, lipase, proteases, trypsin, chymotrypsin, after they've done their job digesting the food, you then digest those enzymes. Did you know that 40% of the protein in the human diet is your own digestive enzymes? Wow, it's like going to a restaurant where after you eat your food and the waiter's done for the night, you carve him up and eat the waiter. Wow, that's amylase, lipase, and protease. 40% of the protein in the human diet is your own digestive enzymes. Well, this is a very nice picture that it's one of those things that if you understand it all, looks terribly clear. And if you've never studied it all, looks terribly busy. This is showing the cycle that bile acids are turned into bile salts. Now, bile acids are made out of cholesterol. Now, I know we think of cholesterol as some very bad thing that's damaging, going to kill you, clog up your coronaries, and die. But if you didn't have cholesterol, you'd die. You would not be able to have any steroid hormones with the exception of thyroid hormone, because all the steroid hormones are made out of cholesterol. Progesterone is out of cholesterol. Testosterone is made out of cholesterol. Aldosterone, progesterone, testosterone are all made out of cholesterol. Vitamin D, cholecalciferol, cholecalciferol, cholecalciferol. Doesn't that sound an awful lot like cholesterol? Cholecalciferol, cholesterol, cholecalciferol. Oh, yes. So cholesterol is an indispensable substance for our body, without which you couldn't make bile acids. No bile acids or salts, you can't absorb fat and you die. So bile acids, cholic acid, and quinodeoxycholic acid, get sugar-coated. Just a spoonful of sugar makes the bile salt go down, the bile salt go down. Spoonful of sugar, the glycine and the taurine, make the bile acids turn into bile salts. And it's the bile salts are the ones that are the water-soluble. And then they get stored in the gallbladder, and inside the gallbladder, everything is reabsorbed except bile salts. Everything is reabsorbed except bile salts and bile. Sodium is absorbed, water is absorbed, chloride is absorbed, and what ends up happening is that the bile concentrates itself. Bile gets concentrated. Bile gets concentrated and waiting for the cholecystokinin to constrict the gallbladder. Now, this can be very confusing to beginners, but confusing it with bilirubin. Now, bilirubin is also stored in the gallbladder. Bilirubin is also conjugated and sugar-coated. Bilirubin, though, has no functional purpose. Bilirubin is hemoglobin poo-poo, hemoglobin scata, hemoglobin garbage, and it's simply being taken out with the garbage in your gallbladder. So bilirubin and bile are easy to confuse. They are both conjugated in the liver, they're both stored in the gallbladder, and they both get sugar-coated. They're both named Bill, but they're very confused. It's like the difference between Bill O'Reilly and Bill Clinton. They are very different functions, but they may both start out with the same first name. Everything gets concentrated in the bile, but salt and water are reabsorbed. Now, after the fat is absorbed, the bilirubin is excreted, but the bile salts and bile acids are recycled. Bilirubin's excreted, but bile is recycled. Bilirubin, garbage. Bile, good. Bile acids of cholic acid and chenodeoxycholic acid get synthesized in the liver from cholesterol. Lipid-soluble bile acids get conjugated primarily with glycine, sometimes taurine. They get water-soluble. Look, children, it's how you make soap, okay? You're taking fat. You ever try and wash butter off your hands with water? You can't. The bile is soap. It saponifies it into little micelles. It's no different than soap, so you can wash oil off your hands, okay? The conjugated bile acids are the soap, so that you basically make the fats water-soluble and the things can get absorbed. Other than that, you couldn't break it up into small enough micelles for lipase to touch. You got to get into little itty-bitty little droplets, and that lipase would never be able to touch and dissolve it up. Secondary bile acids just mean that the bile salts get decomposed. That's all. Literally what happens is that it's what makes stool brown. Cholic acid gets turned to deoxycholic acid and lithocholic acid. And it's really just saying what happens when they get oxidized and they're going to depart and turn the stool brown. That's all. It's just a little food coloring, little stool cosmetics, I suppose. Micelle is a $5 word for droplet. The same way, if you're on an airline, you ever notice how the ice cubes have holes in them? They have holes in them, creates more surface area, cools things down faster, and you don't have to carry as much. That's right. So as water is heavy. I think it's about 2.2 pounds a liter, don't you think? Yes, that's what a kilogram is. A liter is 2.2 pounds a kilogram. A liter weighs a kilogram. So you want to have more surface area. That's why ice chips have more surface area. So micelles are little droplets of fat. And the concentrated bile salts end up with little water-soluble spheres with a lipid-soluble interior. And they transport lipid-soluble materials into the aqueous medium of the bile fluid in the small intestine. Well, the other part is this. Are you mostly watery inside you or mostly fat? What are you inside the body? The body inside, particularly the bloodstream, is mostly water. Mostly water. Well, how do you get these fats into your watery world? Well, you've got to cover them up with some things that are water-soluble on the outside and fat-soluble on the inside. And that's what micelles are. Micelles are little fat droplets. And they're able to be covered with bile and be water-soluble on the outside simply to make it into the body. Now, they are absolutely indispensable because without the micelles, which are so small, you would never have the surface area with which to dissolve anything, and the lipase would not touch. Ultimately, what can happen with the micelles is that only in the distal ileum can the bile salts get actively reabsorbed and recycled. Did you know that within one meal your bile salts can be recycled 2 or even 3 times? Wow, you mean you're recycling yourself? Wow, it's like washing your plates and serving food, then washing your plates and reserving food with the same plates. Wowie gazowie, that's efficient. So without the reabsorbing mechanisms and you having loss in the stool, if you get deficiency in bile salts, you get big fat malabsorption and you get cholesterol gallstones. Now, as a cause of pancreatitis, which one's going up? Alcohol or gallstones? Are we more drunk than we used to be, or are we more stoned? We're more stoned. We get more stones because of pancreatitis because we're fatter than ever and we don't have enough bile to cover up all our cholesterol. So we start forming cholesterol gallstones more because we're simply more fat than we used to be. Bilirubin is a lipid-soluble metabolite of hemoglobin. That's a fancy word for saying garbage. It gets transported to the liver and attached to protein. It gets conjugated, and it gets excreted as water-soluble glucuronides because it's water-soluble and gives a beautiful golden yellow color to the bile. It makes it sound tasty, doesn't it? My goodness, makes it sound like butter pecan ice cream. No, it's trash. Stercobilin also makes it turn into trashy look too. It helps make the stool brown. Do you ever wonder, you see that, what you can say to your friends? What are you learning in medical school that I don't know? And you could say, why is the day bright? Why is the sky blue? Why is the stool brown? Bicarbonate is secreted by the liver. Now, most people don't think of the liver as a bicarbonate-secreting organ, but it is. This is the difference between the person who gets a 240 and a 260. Person at 240 says, well, I know that secretin makes bicarb out of that pancreas. And the pancreas makes the bicarb. And then acid touches the duodenum. Duodenum makes the secretin. The secretin makes the pancreas make bicarb. But secretin also makes bicarb out of the liver. And there's a pumping of sodium out of the gallbladder where sodium and water and all the electrolytes come out, but the bile gets concentrated. And it's not just the bile that gets concentrated, it's bile salts, bile pigments, and bilirubin. Everything gets concentrated in the gallbladder. Everything except the salt and water. The salt and water get pulled out. The bile, the bilirubin stay behind. One of the major components is a phospholipid, like lecithin. It becomes insoluble in water, but it's solubilized by the bile salt micelles. Cholesterol is present in small amounts because most of the cholesterol that's in bile should be converted into bile acids and bile salts. So free cholesterol should be in small amounts because cholesterol is insoluble in water just as fat is insoluble in water. It's got to be solubilized by the bile salt micelles before it can be secreted into the bile. So we don't want a lot of free cholesterol running around because that's how you get cholesterol gallstones. And that's no good. Secretin causes secretion of bicarb and fluid into the bile canalicular ducts. It's a direct effect of secretin on the liver. And the secretion of the bile salts by the hepatocytes is directly proportional to the portal vein concentration of bile salts. Yes, it is. So cholecystokinin causes gallbladder contraction. That's what the word means. Gallbladder contraction, gallbladder action, and opening up the sphincter of Oddi so it can relax and the gallbladder can contract and its contents get ejaculated through the common bile duct. Now, you might say through the entire course of human history, why are gallstones such a big problem? Seemingly only now. In the Ebers Papyrus and Maimonides, they didn't talk about gallstones. The reason is because people were just not so fat for hundreds of years into the past. The idea of being able to have unrelenting exposure morning, noon, and night to meat and animal products and fat, well, all those gallstones are a direct result of fat and meat consumption. There is nothing about us that's a carnivore biologically. Now, I happen to like eating a lot of raw meat, frankly, and so I'm an A+ carnivore. But biologically, I know I'm going against my own physiology. Herbivores have flat teeth that grind. We have flat teeth. We don't have sharp, ripping teeth like a carnivore. Herbivores are used to maintaining a very low cholesterol, a very low LDL. We die at a high cholesterol. We die at a high LDL. We die with it because it clogs up our coronaries, our carotids, our brain, and we also make cholesterol gallstones. Herbivores have long GI tracts, dozens of feet long, like ours is. Carnivores have short GI tracts, and carnivores can live at a very high LDL. They need the energy. So everything about us biologically is not a carnivore, not even an omnivore. Biologically and physiologically, we are herbivores. We are herbivores masquerading as carnivores. Why do we need microvilli? Villi and microvilli in general increase surface area. So the water and the electrolyte reabsorption is greatest at the villus tip. And the secretion is greatest in the crypts. How interesting. I reabsorb at the tip and I secrete at the crypts. But all of these things are meant to increase surface area. Here's a nifty picture of the crypts which do the secretion. You notice that chloride is going into the lumen. That's the channel that gets switched on in cholera. And it's the channel that gets switched off in cystic fibrosis. Now, the other thing you'll notice about this is a 2-chloride sodium-potassium channel. A 2-chloride sodium-potassium channel. Where else do you know of a 2-chloride sodium-potassium channel? That's the same as in the thick ascending limb of the loop of Henle. It's the same as in the thick ascending limb of the loop of Henle. But this one is not affected by loop diuretics. So furosemide, bumetanide, and ethacrenic acid have no effect on it inside the guts. We reabsorb at the tips. We secrete in the crypts. 2-chloride sodium-potassium transporter in the basolateral membrane, and you get ion uptake by secondary active transport, and the sodium entry drives potassium and chloride against their electrochemical gradients. And that's why it makes you have a negative intracellular potential, so it pushes the chloride through. And this is the mechanism of secretory diarrhea. Secretory diarrhea, such as from invasive bacterial entities. Luminal chloride pulls water and sodium and the other ions into the lumen. Why? Because chloride is negatively charged, isn't it? And sodium is positively charged. Also, it's increased by vasoactive intestinal peptide and acetylcholine. That's why it's called vasoactive intestinal peptide, because it increases the secretions, because it's vasoactively active in the intestines. The chloride channels get opened up by cytosolic calcium or cyclic AMP and cyclic GMP for that matter. So those are both second messengers for the activity of those channels. And the cyclic AMP dependent calcium channels are the same thing that's affected by people who have cystic fibrosis.